Hi guys. So this is going to be how impulse changes momentum. We talked yesterday about momentum and impulse, and how momentum is moving inertia, and impulse is a change in momentum, which is the result of a change in velocity typically. You can also have a change in momentum by a change in mass, such as an object breaking into pieces. But you also have, more than likely, it's just a change in velocity of the object, like a golf ball being hit by a club or a baseball being hit by a bat. The object changes its momentum due to the impulse acted upon it, which is a force over a period of time. So, to have the greatest change in momentum, to increase momentum, you want to apply a force through a long duration of contact. So, if you've ever heard the term following through, playing baseball or golf, I'm not sure other sports that pertain to that, but those two do. The longer you are pushing on the ball, you're following through, you're applying force over that period of time to the ball, which increases the amount of that momentum change. So if I have a momentum of 10 and I apply a force, I might change that momentum to 20. If I apply that force over a longer period of time, I might change the momentum to 30. And so, as depending on what you're trying to do, you may want to make the momentum change the greatest or the smallest. Bunting in baseball is when you hit the ball as little as possible. You don't swing the bat, you hold it and let the ball just bounce off. And that gives the minimum amount of change in momentum. And versus a follow through, which where you hit it very hard, well, assuming you hit it very hard and follow through, giving you a large change in momentum to try to hit the baseball very far into the field. All right, so here's a question which kind of tests that understanding. A cannonball shot from a cannon with a long barrel will emerge with a greater speed because the cannonball receives a greater what? The longer the barrel of any weapon, the further the projectile can travel compared to a shorter barrel. So the rifles that snipers use to shoot great distances are very long. And that's one of the features that enable them to shoot that projectile a long distance precisely. So, just mentioned above, we talked about impulse being force over time and that an impulse causes a change in momentum. So, a long cannon will cause the cannonball to gain a greater speed, which is how I said momentum change is most often done is with a larger change with a change in velocity. And the greater impulse will cause that cannonball to travel faster. Now, average force, the force itself is the same. It's the amount of time in which it is delivered. So the answer would definitely be B. Even though it's tempting to say that it's both, it's only impulse. All right, case 2, decreasing momentum over a long time, which is essentially, it's kind of the opposite. So if I want to change momentum a lot, I want to increase the time in which that force is applied. So I'm following through on my pitch, I'm following through on my golf swing. But when it comes to decreasing momentum, an example of why that isn't needed characteristic or property is like a vehicle stopping. Okay, so if you've ever been in a car with a new driver or someone who's just a bit of an aggressive driver, they hit the brakes a little hard sometimes coming up to a stop sign. So if you wait till the last minute, you have to apply a large force over a short time, which would be a large impulse, versus if you applied that same, you could apply much less force over a longer period of time and achieve the same change in momentum, but without experiencing as much of an impact. So a fast-moving car hitting a haystack or a cement wall produces different results. Do they both have the same change in momentum? Yes. Do they both experience the same force? No. Do they experience the same impulse? Yes. So the change in momentum, so both cars, regardless, hitting a haystack or a cement wall, have the same starting velocity. All right, let me use this equation to help explain this. So change in momentum is the final momentum minus the initial momentum. So final momentum is just the mass times the final velocity. The initial momentum is the mass times the initial velocity. So if I have an initial velocity, let's say of 60, when I stop, I'm going to have a velocity of 0. Now, if I stop suddenly or over time, I'm still going to go from 60 to 0. And this applies to the stop sign thing too I was talking about. Whatever speed you're going initially, you're still going to go to 0 either way. The difference is how long that change occurs over. So change in momentum is equal to final minus initial. And if the final velocity is 0 either way, then we have a fixed change in momentum. So regardless of how the vehicle stops, the change in momentum will be the same number. Change in momentum is also equal to impulse. So this is equal to this. So since we know that change in momentum is the same either way, because the only thing we're changing is how quickly it stops, we're not changing the initial and final velocity. So change in momentum is constant, which means that impulse is constant, which means that the force times time will have the same value either way. The key difference here, though, is the time it takes to stop. So if you hit a haystack, it's going to take a larger amount of time. So if time is large, then the force will be less. Remember that impulse can't change because the change in momentum is fixed. Change in momentum is equal to impulse, so that is fixed. The only variable that can change as a result of increased time is a decrease in force. In the case of the cement wall, that would be stopping over a short period of time, right? So that would be a smaller time, which means the force would be increased. So the question is, would they have the same momentum? Yes, they would have the same change in momentum. Would they have the same impulse? Yes, because by definition, change in momentum is equal to impulse. And then do both experience the same force? And this is where they're different. This is not, that would be false. They do not experience the same force, which is why it's different, hitting a haystack and stopping versus hitting a cement wall. So if you ever are in a situation where you know you're going to crash, it's much safer to hit something that will take you longer to stop versus stopping suddenly, which means like avoiding hitting trees, rocks, cement walls, etc. Okay. All right. When a dish falls, will the change in momentum be less if it lands on carpet than if it lands on a hard floor? Now, we know that there's a difference between landing on carpet or a hard floor. In fact, if you've ever dropped a plate or something in your kitchen, typically you have a tile floor, wood floor, linoleum floor, something like that. Versus if you dropped a plate like in the living room where you might have carpet, you might have noticed that, you know, you're just instinctually less worried about it hitting the carpet than a hard floor. And so, yes, it's different, but let's look very carefully at what the question is. It even tells you to be careful. It says, is the change in momentum different? So if I have an object that is in free fall and it's going to land on the floor, it has an initial velocity of whatever. Let's say it has a velocity of 0. And then right before it hits the ground, it's going to have some velocity. Okay. I'm going to call this velocity 2 just for the sake of clarity. And then it's going to stop. And that final velocity is going to be 0. Okay. So it's going to start at 0 because you're dropping it, let's say. And then there's going to be some speed right before it hits the ground, and then it's going to stop. So your change in momentum is going to be a fixed value regardless of where it lands. So if it lands on carpet or if it lands on tile, it's going to have the same change in momentum, because remember that momentum is mass times change in momentum is mass times final velocity minus mass times initial velocity. So the initial velocity would be whatever the speed is right before impact, so v2, and then final velocity would be 0 if we're talking about something that's stopping. So this change in momentum will be constant regardless of how the object stops, because the determination for change in momentum is simply that it stops, that velocity goes from some value to 0. So will the change in momentum be less if it lands on the carpet? The answer would be no, they're both the same. If we're talking about force, that's different, but we're talking about here change in momentum, and that is not based on what it lands on, just that it lands. This image is showing us the comparison of in this case, a truck hitting a haystack versus hitting a concrete wall. Both start off with a high velocity. When striking the haystack, the vehicle slows over a long period of time, therefore having a smaller force. But when it hits a concrete wall, it stops in a short period of time and therefore has a large force. The impulse is the same either way, because you're going from a starting velocity to 0, but the amount of time you take to stop is the variable that you can control and can change the amount of force, which would be the impact of the stopping. So the same vehicle going the same speed can crash and not injure you, or crash and injure you. This is also the property behind padded dashboards, airbags in cars, bumpers that crunch. They're all designed to increase the time it takes for something to stop, therefore reducing the impact force. So an airbag, it opens so that your face doesn't stop like this on the steering wheel, but that it hits over a longer period of time. It's only millisecond. It's less than a second, I believe. It's milliseconds, but that's enough time to reduce the impact force to potentially have less damage done to your face. So that's the physics behind why we have airbags and padded dashboards and so on. Okay. All right, another example. In jumping, you bend your knees when your feet make contact with the ground, because the extension of time during your momentum decrease reduces the force on you. So if you jump from a high height and you lock your knees, you have a way higher chance of breaking your legs versus if you bend your knees and essentially slow down your stop. People have even been known to survive parachute failures by landing and rolling as opposed to just stopping. So if you land, bend, roll, your stopping happens over a longer period of time, which reduces the force of impact, versus if you just go stop. In boxing, it's you ride with the punch. So it's better for you to instead of going face, you go face. You follow, you back away from the punch as it's coming at you, and that causes the time to be extended and therefore the force decreased. Another example of decreasing momentum and manipulating that time interval to change the impact force is in karate or other type of similar sports where you're breaking bricks or breaking boards. And the trick is that the time of impact is very short. This increases the force that you're able to supply. So your change in momentum, your mass times velocity, that change is fixed. You can maximize it, obviously, but there's only so much that you can put into it. But if you hesitate and apply that force over a short period, over a longer period of time, it's possibly not enough force to break the bricks and therefore injuring you more than if you hit it hard, basically hit it faster, and therefore reducing the amount of force you need to break the bricks. So I still don't feel comfortable with it personally. I know that there are people who do it, and to me, it still sounds insane, but I know people do it. So maybe you have some personal experience doing that as well and can attest to the fact that you definitely don't want to hesitate at the last second. All right, the last concept is the law of conservation of momentum. In the absence of external force, the momentum of a system remains unchanged. So let me show you what this means. Okay, so the red is representing the cannonball and the blue is representing the cannon. Initially, before the cannon is fired, they are both not moving. So the velocity would be 0. So regardless of mass, the momentum of the cannonball and the cannon before shooting is 0. So it's 0 on the left side of this equation. Then on the right side, we have the mass of the cannonball times its final velocity and the mass of the cannon times its final velocity, and we're going to add it. Now, it seems like initially that this is not going to equal 0, but here's the kicker. Velocity is a vector quantity, which means it has direction. And so if we define just like a XY plot, that to the right is positive and to the left is negative, what we will find is that the velocity of the cannon will be negative because it'll go backward. That recoil we talked about will be, so this velocity will be negative, and the cannonball will move to the right, which would make its velocity positive. So the mass times velocity of the cannonball plus the mass times velocity of the cannon will actually add up to 0. And this is called the law of conservation of momentum, that for a closed system, so in other words, we're not taking into account other things, just the cannon and the cannonball, that if it has this momentum initially, which is 0, then it will remain 0 even after the shooting of the cannon. Now, the cannonball is lighter, but it's also faster. And so the difference, so the mass of the cannonball would be small, the velocity would be large, and then the mass of the cannon would be large and the velocity would be small. The result of this being negative and this being positive is that this would actually add up to 0, fulfilling the law of conservation of momentum. All right, you're going to work through this practice page next. Read each question carefully and apply the concepts that we've learned so far. Momentum is mass times velocity. The equation for that, once again, was P equals M times V. This is just for momentum. We also know that change in momentum is the final minus the initial momentum. So that can be written as mv final minus mv initial. And then we know that change in momentum is also equal to impulse, and impulse is equal to the force applied times the time of application of force. Okay, number 1, a moving car has momentum. If it moves twice as fast, its momentum is blank as much. So my recommendation is to use the plug-in method for determining how something changes. So I like to just do 1, 1. So 1 times 1 equals 1. And then if I double the speed or the velocity, then that would make this 2. Mass would be 1. So then momentum would be 2, which means that it doubled. Next question, 2 cars, one twice as heavy as the other, move down the hill at the same speed. Compared to the lighter car, the momentum of the heavier car is blank as much. So same concept, except instead of mass doubling, instead of force velocity doubling, we're doubling mass. But same question as the one above. Next question, the recoil momentum of a gun that kicks is more than, less than, or same as the momentum of the bullet it fires. Note that it is talking about the momentum difference, not the velocity difference. So one of them is different and one of them is the same. Remembering, of course, that they have different masses, and that's the result. That's why those are different. Next one, if a man firmly holds a gun when fired, the momentum of the bullet is equal to the recoil, the momentum. Oh, I already actually. Those two are similar. The recoil momentum of a gun that kicks is more or less than. So that's the conservation of momentum we talked about. If the initial momentum is 0, then the momentum of the two objects after would have to also be equal. If a man firmly holds a gun when fired, the momentum of the bullet is equal to the recoil momentum of the what? Suppose you're traveling in a bus on a highway speed in a nice summer day, and the momentum of an unlucky bug has suddenly changed as it splatters onto the front window. Compared to the force that acts on the bug, how much force acts on the bus? So this is not only the concept of momentum, but also the concept of action-reaction forces. So the bug cannot hit the bus harder than the bus hits the bug. That's action-reaction force. And the time that the bug hits the bus is the same amount of time as the bus hits the bug. So the impact would have to be the same. So then we also have a change in acceleration, which suffers the greater damage. So these are thinkers. You want to think through this, look at the equations, try to kind of suss out what is actually going on here. The next page, you are testing that the conservation of momentum. So you're given a certain amount of data here, and then you're asked to fill in the missing pieces. And so the first thing is that Granny's mass is 80 kilograms and her speed is 3 meters per second, which means that her momentum would be mass times speed. And then Ambrose's mass is 40 and his speed is 0, so his momentum would be 0. The total momentum would be Granny's momentum plus Ambrose's momentum. So that would be the system. Then she picks him up instead of crashing into him. And so after the collision, does Granny's speed increase or decrease? After the collision, does Ambrose's speed increase or decrease? After the collision, what is the total mass of Granny and Ambrose? So we can do that one really quick here. 80 plus 40, so 120. After collision, what is the total momentum of Granny and Ambrose? Now, based on the law of conservation of momentum, the total momentum does not change. So whatever the total was before is the same total as after. Use the conservation of momentum law to find the speed of Granny and Ambrose together after the collision. And that equation I shared with you before, but I'm going to write it here at the bottom right now. All right, so here's the equation for this particular type of collision. Mass of Granny times initial velocity plus mass of Ambrose times initial velocity. Ambrose had an initial velocity of 0, so this part comes out to 0. And then that's equal to the mass of Granny plus Ambrose because she picks him up, so they become one system. And then whatever the final velocity is. So you can use this equation to determine the final velocity of Granny and Ambrose. So you have the mass and initial velocity of Granny here. You have the mass and velocity initial for Ambrose here, which comes out to 0. And then you have the mass of Granny plus Ambrose, which we found to be 120 kilograms. And then final velocity is what you're solving for.